I have this handout linked for you if you just want to print that out, or you can write it down in your own notebook paper there. That's up to you. But we have three brand new properties that are similar to some things we did before. You already know how to do the derivatives and integrals involving e's and the ln, the natural log, the natural exponential expression there. What we're going to learn this section is how to do the derivatives and integrals with like a number raised to a power instead of just e. So like 5 raised to a power. Here, if we instead of natural log derivative, we'll have like log base 17 or something like that. Instead of the integral of e to the x's, we'll have the integral of like 7 to the x, things of that nature there. So just different bases. And so these are your three new properties in these cloud things at the top there. So when you take the derivative of a number raised to a power, that's what the a is, just representative of a number there. You're going to do the number raised to that power, just rewrite it, times it by the derivative of that power, times it by the natural log of whatever that base is. So if you have 5 raised to a power, you're going to go 5 to that power, just rewrite it, times by the derivative of that power, which is a 2x. And then if you have a base other than e, you got to tag on the ln of 5, and then that's it. So what we learned before, this second example, you already know how to do. I just want to show to you how these are connected and why we didn't really need to worry about that when we learned e to a power. So remember with the derivative of e to a power, you go e to that power times by the derivative of that power, and then we just stop. Technically, you can use this property as well, but if you do the ln of that base, the ln of e is just equal to 1, which is, and that's, since that's 1, we just didn't really need to worry about that in the past there, and those e's pop up a lot more often, so we don't need to worry about that extra piece. But you do need to worry about that extra piece where you have something different other than that e right there. So there's your property. And then what we know is if you have the natural log of something, you go 1 over that stuff times it by the derivative of that stuff. So if you have log base a, so just any base, okay, what you're going to do, you're going to go 1 over that stuff, you're going to times it by the derivative of that stuff on the top, and then on the bottom, what you got to remember to tag on is the ln of whatever that base is, and you got to remember it goes in the denominator. So if you have log base 7 of x cubed, and I want to do the derivative here, so I'm going to go 1 over that x cubed, so it goes to the bottom, I'll times it by the derivative of x cubed, which is 3x squared on the top, and then if you have a base other than e, you just got to tag on the ln of 7 in that bottom part in the denominator, and then you just simplify it, and then you're done. So what we already did before, if you have the ln of something, you would go 1 over that stuff times it by the derivative of that stuff, and you would just get 3 over x right away. But you can technically use this property. It works for any base, but we didn't really need that before because the ln of e was equal to 1. All right, and then when you do the integrals with these different bases, if you have the integral of a to a number, you're going to get a to that number divided by the ln of that base. Okay, now you have to be really careful with the balancing. So if you have like 5 to the 7x, let the u equal to 7x, right? So we'll talk about that. So the basic properties, if you have the integral of 5 to the x, just straight integrate that. You can go straight to the answer and get 5 to the x, but then you just have to balance that with the ln of that 5 right there, the ln of that base. If I had like a 5 to the 2x, I would let the u equal to 2x, the du is equal to 2, balance the 2 at the 1/2, and you have the integral of 5 to the u, which you would get 5 to the u over ln of 5, and then you'd have that 1/2 just out there as well, so you just have an extra 2 in that denominator there, okay? Right here, if you have these exponential expressions, if you ever get stuck, I said the approach is just like when we learned the integral of e's to u's, where I remember in the last section I stressed, if you have a single e in the integral, let the u equal the power. If you have multiple e's in that integral, let it equal the entire exponential expression or the entire inside the parentheses or the denominator, something like that. So if you ever get stuck with the numbers, like what should I let u equal? And just pretend that's like an e for a second. Like if you have e to the sine of x times cosine of x, well, we stressed in the last section that if you have a single e in the problem, let the u equal the power. So if you have a single one of these exponential expressions in the problem, let the u equal the power, then most likely is going to work out very, very well for you. So if you let the u equal that weird power, do the derivative, you get the squiggles to match up, there's nothing to balance. And then now you have the integral of 2 to the u, and so now you're just going to use your property. You're going to get 2 to the u divided by the ln of that base, and then you can plug your x's back in. If it's an indefinite integral, remember your plus c, and then you're done there. So this is the only one where the ln is just on the outside. Both of these, the ln is in the denominator. So sometimes I have people like stick this ln of 7 up on the top, or this ln of 2 up on the top, or something like that. So I guess just what helps me to remember that, I know when I do the derivative of e to a power, I just go e to that power times the derivative of that power. There's typically, not a denominator involved, but like when you do the derivative of the ln of something, we know we go 1 over that something, right? So since you're kind of creating that fraction here, it just kind of helps me. I usually involve fractions with the ln's and the log derivatives So that's what helps me remember to stick that element of a in the denominator. And a lot of times when I do the integrals, we do balancing with reciprocals, and you create the fractions when you do your balancing. So that's another thing, since I'm creating like a fraction there sometimes there, that's what kind of helps me. Just a couple of little tricks there that maybe help you remember that those go in the denominator. So whatever works in your brain there, or just straight up memorize that, then you're going to be good there. All right, the last thing, we're going to do this example together. Last thing. So these are just properties where you can go straight to the answer right there. So what we know, if I have a variable raised to a number, I can integrate that and go straight to the answer. Multiply by the power decrease power by 1. Now we just learned if I have a number raised to a power, I can do that number raised to the power times about the derivative of that power, which is 1, tag on the element of that base right there. So that's that brand new property we just learned. So if you have a number to a letter or a letter to a number, we can go ahead and go straight to those answers there. What we're not ever going to be able to go straight to the answer on is if you have a letter to a letter, a variable to a variable. So if you have a variable to a variable, a lot of times I have people get 0 points or stuff like this. They will go ahead and like multiply by the power, decrease the power by 1, just make up their own like weird stuff right there. It doesn't quite make any sense, right? So what we want to do is, if you have a variable to a variable, now the homework might tell you to kind of use logarithmic differentiation. I'm never going to tell you when to use this. Just if you're in a testing situation, if you say a variable to a variable, that's what gives it away. That's when you know to do this stuff, right? And so when you have the variable, since we don't have a property to go straight to the answer in, logarithmic differentiation is actually something pretty easy. Just what you did last year when you had equations that you had to solve involving the variables. What we're going to do here is just take the log of both sides. That's what logarithmic differentiation is. So I'm just going to do the natural log of both sides. I always do the natural log because you can see it's easier to do the derivative of the natural log versus like the different bases there. So you know, this just going to make that easier on us as if we just stick with the natural log. And then so then I'm going to get the natural log of y on this side. And then here, if I have the natural log of something raised to a power, remember our pre-calc properties, we're allowed to bring that power down in front. And we have x squared ln of x. And so your original problem had a variable to a variable, which we cannot do the derivative of, but the fact that we just did the natural log of both sides and carried that exponent down in front, now I no longer have a variable to a variable, and now I should be able to take the derivative of this thing. So if I don't have y equals, remember this is an implicit differentiation problem, we're going to take the derivative of everything as is. If I take the derivative of y is when it, tag on a y prime. So the derivative of natural log of y, we're just going to go 1 over y, but I took the derivative of y's in it, so I got to tag on a y prime. This is a product right here, which means we got to use the product rule. So we're going to go first function times by the derivative of the second. Derivative ln of x is just 1 over x, plus the second function times it by the derivative of the first, which is a 2x. And then what we usually do is just simplify this side. A lot of times here we might have something we could factor, like a GCF with the variables. We might have a couple fractions where we want to get ourselves one single fraction. So you just got to look at what you have there and just simplify that like we've been doing all year. But this is just a single x right here. X squared over x is just going to be a single x. And then so what I'm looking at when we normally do derivatives, if like I said, if we have different fractions, get one single fraction. If I have GCF, we could do with the letters. Go ahead and do that GCF. So we can factor out an x. And then we have this 1 over y, y prime is equal to that. And our ultimate goal is to solve for the y prime. So I'm going to multiply both sides by the y. And we are almost done here. We can't leave the y in the original problem. You must get rid of the y, all right? You got to get rid of that y that's in there. And the way you're going to do that is you're going to use the original function. The original function told us y is equivalent to this. So you're going to take that and stick that in right there. Now there's two possible answers that we got to be prepared for. This is one possible answer that if you're taking one of my assessments, I would accept this right here for full credit. Sometimes on the AP test, these will be like a multiple choice thing. Sometimes it'll pop up on the free response there. Sometimes if it's on the multiple choice, sometimes this will be an answer choice. Sometimes it will not be an answer choice. So here's one other thing that they possibly do, and we just got to be prepared to do both just in case, because I've seen either or. If that's not there, before I choose like none of these or just, go into the different problem, One algebra thing that you could do here, see how this is x to the first and this is x to some power. So just like your algebra 1 days, if you have x to the second times x to the third, you're allowed to add those exponents up and make that x to the fifth. So if I wanted to on this one, another possibility is to just leave that parentheses alone. And then right here, I would just go x to the 1 plus that x squared, and I would just add those exponents up. And so either answer would be acceptable for me. And I might even want to put that in parentheses, just hey, that's all in one exponent there. But all they did is just add up the exponents, just a basic algebra 1 problem there. So like I said, I've seen AP multiple choice where they did stop right there or where they did do that differently. So I just want to share with you both of those. Okay, so I think the stuff in this section is pretty straightforward, but you just have to kind of know those properties. And since we're keep giving you a bunch of different properties in this chapter, what I have for you, my students in the past have always told me this thing has been pretty valuable for you. But in their calendar, I linked something called a blue sheet review. That's essentially just a study guide. And this kind of just helps me when I study it. I just like to write everything out. Some of you might like to make your own note cards and do flashcards like that. The way my brain works, I like to just write everything on one sheet of paper and then just have all that on there so I can study that. But it has like your e to a power, your natural log. It has your new properties that we just learned today. And then what we learned in the past, just how to do the derivatives and integrals. It also has your trig integrals on there that we learned. What you might want to add to the side here is just your trig derivatives from our derivative chapter there. And then you just kind of have all those on there. And then the other side of that, we'll have something we're going to learn in the next section, like how to take a derivative of the inverse trig functions and how to integrate things with the inverse trig functions into these paths. But this stuff we haven't quite, we'll learn that stuff in the future right there.